Hello everyone, how are you all? I hope you all are fine by grace of God. I'm also fine here. I'm here today to explain to you the derivation of equations of motion by method of integration. So the equations of motion in the chapter of motion in one dimension are, first one is v equal to u plus at. The second one is s equal to ut plus half at square. The third one is v square equal to u square plus 2as. Another one is found to come, that is s nth equal to u plus half a all multiplied by 2n minus 1. So these are basically the equations of motion of a body moving under constant acceleration. There's an important point to be noted, keep it in mind. If and only if the body is moving under constant acceleration, then and then only these equations are going to be applicable. Then and then only these equations are going to hold true. As soon as the acceleration has started changing, then only these equations are going to be invalid. These equations are going to be violated. Alright, keep it in mind, that's an important point to be noted. So the fact is that here are a few symbols which have been used in representing the equations of motion, which we need to know. Okay, which symbol symbolizes which quantity? So first one, u, is actually the initial velocity, and v is actually the final velocity. And what is a? I told you already that it is constant acceleration. Acceleration has to be constant always. T equal to the time of acceleration. Keep it in mind that t is only the time period for which the body is moving under constant acceleration. For example, if the body is moving for some time with constant acceleration, after that the acceleration started varying, then the time for which the body is moving with variable acceleration is not counted in this time. Keep it in mind. So t can correctly be said to be the time of acceleration. And what is s? S is displacement. Keep it in mind, s is displacement that the body is traveling in time t. What else is there? S nth is another thing which is coming. S nth. Okay, and that is displacement in nth second. Is nth second. Displacement in nth second, that has to be clarified to you a little bit. Nth second means in one particular second. Okay, and that is nth second. Nth second means in one particular second, which is after n minus 1 seconds. Is it clear? So for example, I'm telling you in the 4th second, for n equal to 4, for n equal to 4 seconds, s nth means s fourth, means the amount of displacement that the body is covering in the 4th second. Means for the first 3 seconds the body has moved, and that is some amount of displacement, and after that in the next 1 second it is again covering some amount of displacement. So that is after the end of the 3rd second, for the next 1 second it is covering some amount of displacement, that is in the 4th second, and that is what s fourth stands for. I hope it is making sense to you now. So s nth is the amount of displacement is the nth second. So that is what we have to get here. The expression for that will come out to be u plus half a into 2n minus 1. U is initial velocity, v is final velocity, a is a constant or uniform acceleration, t is the time period of acceleration, s is displacement in time t, and s nth is displacement in that particular nth second. Alright. So without any further ado, let's come to the derivation by method of integration. First of all, in order to prove the first equation of motion, we have to start from the definition of acceleration. Acceleration is defined as the change in velocity by the change in time. Alright, so that is what acceleration is. The rate of change of velocity with time is called acceleration. That is written in language of differentiation as dv by dt. dv by dt. So where dv and dt are the infinitesimally small values of velocity and time, right? Right from here you are getting dv equal to a dt. So right in this step you have to integrate both sides, and that is what we can do always in mathematics, integrating both sides of an equation simultaneously. So now imagine the case that the body was going with initial velocity which is u, and a force was applied on the body, as a result of which the initial velocity has changed to v over here. Okay, so this is the velocity of the body at time t equal to 0. This is the velocity of the body at time t equal to t, because the time interval after which the velocity has changed from u to v is t. That is all we are taking here, t, time period for of acceleration, time, the course of time for which the body has moved with constant acceleration. And so we need to put the limits over here. The limit for velocity, the lower limit is u, the upper limit is v, and the limits for time are from 0 to t. Okay, the integration of dv is v, as you know already, as per as I hope. Integration of dx is x, so integration of dv is v, the limits being from u to v. This a is a constant, so it should come out of the integration. It should come out of the integration. So a is remaining, and integration of dt is t from 0 to t. So now the rule is that first we need to put the upper limit minus the lower limit in its place, that is v minus u equal to a into t minus 0. That means v minus u equal to at. Do a side change to get at the result, v equal to u plus at. That is your first equation of motion. We have already ended up getting that. Now in order to prove the second equation of motion, we need to start with the definition of velocity. Velocity is defined as the rate of change of displacement with time, means v equal to delta s by delta t, that in language of differentiation is ds by dt. From here we are getting ds equal to v dt. Right in this step all we have to do is substitute the value of v as u plus at, which we have got already in the earlier equation. That we can surely do. I hope you won't object me doing this. U plus at multiplied by dt, so that is equal to u dt plus at dt. Alright, right in this step we can integrate ds, integration of ds equal to u dt, integrate this, plus at dt, integrate this. What should be the limits of integration? The limit of integration for s is going to be s equal to 0 to s equal to s, right? Because in time t equal to 0, the moment the body has started to move under constant acceleration, its amount of displacement is 0, and after a time interval of t, it has undergone a displacement of s. So So lower limit is 0, upper limit is s. For time, the same limit 0 to t. 0 to t. Right? Now put the constants out of the integration. U dt. Initial velocity u is definitely constant, so that is supposed to come out of integration. Plus a, acceleration is constant acceleration. I told you already earlier, for which all these equations are valid. T dt 0 to t, right? So now integration of ds is s, 0 to s. Integration of dt is t, 0 to t. Integration of t dt is t square by 2. As far as I guess you remember the formula, x to the power n dx equal to x to the power n plus 1 by n plus 1, right? So on the basis of this formula, we are writing this t square by 2, 0 to t, because you can understand t dt means t to the power of 1 dt. So all that is coming here is t to the power 1 plus 1, that is 2, by 1 plus 1, that is 2. Okay. So here s minus 0 equal to u t minus 0 plus a into t square by 2 minus 0 square by 2. So finally you are getting at the result s equal to ut plus half at square, isn't it? And that is your second equation of motion. That is your second equation of motion. Now I am rubbing the board out. So now, in order to prove the third equation of motion, we need to start once again with the definition of acceleration, but in a different way. Definition of acceleration, as I had started to prove the first equation of motion, was a equal to dv dt. So now one point to be noted is that this equation contains dt, so t is going to come as a result of integrating, but the third equation of motion is devoid of t. Surprising thing is that the third equation of motion has only final velocity, initial velocity, acceleration and displacement. So there is displacement which I have to bring in this equation somehow. First equation of motion was containing t, second one was also containing t, the time, the third one is devoid of t, so we have to get rid of this dt somehow. How to do that? So here all we can do is multiplying both the numerator and denominator by ds. See and tell me if I can do that or not. ds by ds, definitely we can do, because multiplying the upper and lower side with the same thing makes the thing unchanged. Now dv by ds into ds by dt. Is it alright, children? So how much is this ds by dt? This ds by dt is definitely the velocity, the rate of change of displacement with time. The definition for velocity is something which was used to derive the second equation of motion, isn't it? After this we can write a equal to v dv ds. This is the relation with which we have to start to approach to prove this third equation of motion. Keep it in mind. To prove the first one, you need to start with a equal to dv by dt. In order to prove the second one, you need to start with v equal to ds by dt. In order to prove the third one, you need to start with A equal to V dV ds. V dV by ds. So these are indeed the equations of motion which are universally applicable, be it constant acceleration or variable acceleration. But the first ones which we are deriving by method of integration are exclusively valid for constant acceleration. If a teacher of yours happens to ask you the equations of motion, then don't make a mistake in telling these equations of motion. No, these are not the actual equations of motion. These are the actual equations of motions. Keep them in mind forever, because these are universally applicable, be it constant acceleration or variable acceleration with which the body is moving. But these are only applicable for constant acceleration. Alright, I hope you all are getting to understand. So right from this expression, we have to approach to prove the third equation of motion. Have a look at how I'm doing. So from here I can write A ds equal to V dV. Alright. After that, integrate both sides. A is constant, it should come out of integration. A into integration of ds equal to integration of V dV. Now the limits for integration, the upper limit and the lower limit here as well. Lower limit and the upper limit of s being 0 to s, that for v is supposed to be from u to v. Okay, that will fetch you to the result A s 0 to s equal to v square by 2, limits being from u to v. So here integration of v dv is v square by 2, that is based on the formula x to the power n dx equal to x to the power n plus 1 by n plus 1. I told you earlier already. So here b to the power 1 dv, b to the power 1 plus 1 whole divided by 1 plus 1. I hope it is clear. So s minus 1, the upper limit minus the lower limit, equal to v square by 2 minus u square by 2. Okay, as equal to v square minus u square by 2, or 2as v square minus u square, and finally v square equal to u square plus 2as, and that's what your third equation of motion is. We have ended up getting that. Have a look. V square equal to u square plus 2as. After that, in trying to prove the fourth equation of motion, that is s nth equal to u plus half a times 2n minus 1, we have to start with the definition of velocity as we did in proving the second equation of motion, because this was also containing s in left hand side, and this one too is containing s in left hand side, only the meaning is different. Here entire amount of displacement in time t, here the amount of displacement in the particular nth second. Alright, so let's start with definition of velocity in terms of differentiation. V equal to ds by dt. So ds equal to v dt means u plus at whole multiplied by dt. First equation of motion I'm substituting here. So ds equal to eu dt plus at dt. Okay, then integrate both sides. U I'm bringing out of the integration right in this step. A is also being taken out of integration because u and a both are constants. The initial velocity with which the body was moving initially is constant. After that, the velocity has started changing, or rather started increasing under the constant acceleration with which the body has moved for time t. So t is something which is variable and s is something which is variable. Okay, the initial velocity is constant. Limits being from Sn minus 1 to Sn. This is going to give you the displacement in that particular nth second, because in total amount of n seconds the body has moved by a displacement Sn. In time 1 second smaller than that, that is in n minus 1 seconds, the body had moved by a displacement Sn minus 1. So in order to get the amount of displacement in the particular last nth second, we need to do the integration from Sn minus 1 to Sn, that is going to give you Snth. Alright, the limits for time are going to be n minus 1 to n, and here also n minus 1 to n. Okay, so here we are getting S Sn minus 1 to Sn, here u t n minus 1 to n plus a t square by 2 n minus 1 to n. Okay, Sn minus Sn minus 1 equal to u n minus n minus 1. Here 2 is being taken out, a by 2, t square means n square minus n minus 1 whole square. Is it clear? This is going to give you Snth. N minus n plus 1, n are cancelled out, a by 2, n square minus, expand in the form of a minus b whole square, a square minus 2n, n square minus 2n means minus minus plus 2n, plus 1 minus plus minus 1. Alright, sign change is being taken care of here. N square are cancelled out. What you are left with is Snth equal to u plus half a multiplied by 2n minus 1. And you have ended up getting your fourth equation of motion, which I had written over here. I hope it was clear. Please see the steps carefully, because a question of 5 marks is bound to come in your examination, where you have to derive these equations of motion by method of calculus. So this is quite important. And so that's all. I hope you could follow clearly all I had tried to explain. In case you still have some doubts, feel free to inform me in the comment sections. Also let me know the topics on which you want me to make videos. And keep studying, stay well, take care, goodbye.